So now we are going to make sense of the secp256k1 specification. So we have already learned about the elliptic curves, modular arithmetic, all the basics. Here we will make use of Fermat's little theorem to understand some certain concepts, right? Yeah. In BIP 137, a new compressed pub key format is specified. So what is a public key, first of all? Public key is simply a point on the elliptic curve. It is generated using the generator point. It has two coordinates, x and y axis value. So each public key is of the form x comma y. So this x value takes 256 bits, which is 32 bytes. Y axis 32 bytes. So in total, it will take about 64 bytes to store a public key. A public key is required in the transaction input, okay, to verify the signature. So this has to be stored in the blockchain. So rather than storing 64 bytes, could we reduce it? Could we only store 32 bytes? Of course, but not exactly. What we will use is, we will use a leading byte plus 32 bytes. So the leading byte will tell whether the format that we are using is compressed or uncompressed. In uncompressed form, we will represent both the x and y axis, hence 64 plus 1, 65 bytes. In the compressed form, okay, we have a choice. The thing is that the public key, it could be either, the idea is, okay, the elliptic curve, it has the form y square is equal to x cube plus 7. This is the mod p, right? So this is the equation that we are trying to solve. Okay, we are using modular arithmetic over p. We are not using real numbers. So this is the equation that we are trying to solve. If x comma y is a solution, x comma minus y will also be a solution. A negative y is nothing but p minus y. So for any pair x comma y, x comma minus y will also be a solution to this elliptic curve. But that doesn't mean that both of them actually generated from the generator point G for the given specific private key. Okay, for the given specific private key, let me just call it PR, private key. Okay, so PR times G, it could be either x comma y or x comma minus y. The verifier has no way of knowing that. So in the leading bit, if the leading byte is 2, then we will know, then the idea is that y is a even integer, right? Because if y is even, like p since p is odd, p minus y will be odd. That's the idea. So if the leading byte is 1, then we can be assured that the y-axis value is an odd integer. So that's the specification laid out in BIP 137. But given the x value, how do you determine this y value? How do we derive the formula, right? How do we take the square root? How does this work in modular arithmetic over p? Remember, we learned in the Fermat's little theorem that a to the power p minus 1 is congruent to 1 mod p. We are going to make use of this formula by, let's say, a simple mathematical trick. That mathematical trick might look confusing to you, but it's actually really very simple. Let's choose the value of k to be x cube plus 7. Right. Now we want to, and let's choose this y value to be k to the power p plus 1 divided by 4. Now you have to ask this question. P is an odd number. P plus 1 will be an even number. Does that mean that number 4 can divide p plus 1 without any remainder? Right? Can this divide it perfectly? Let's try to find the answer to that. So in the specification, this is the value of p which is given. Okay, so the elliptic curve is defined over this prime number field. Right. And it is this exponential form over 2. I have copied this formula into my Python interpreter, and I try to find the remainder of p when divided by 4. So the remainder of p when divided by 4 is 3. So what will be the remainder of p plus 1 when divided by 4? Okay, it will be 0, right? So 4 divides p plus 1 perfectly. So we can be assured that p plus 1 divided by 4 will be an integer. Now the question is whether y square is actually congruent to k mod p. That is the question, because that's what we are trying to solve. Let's try to compute that. So k to the power p plus 1 divided by 4, the whole power 2 will be k to the power p plus 1 divided by 2. This can be rewritten in this form. Okay, k to the power p minus 1 divided by 2 plus 1. So that is equal to, I mean, this is in the exponents, right? So k to the power p minus 1 divided by 2 times k. Now what is k to the power p minus 1? K to the power p minus 1 is congruent to 1 mod p, because this a is arbitrary. For any a less than p greater than 0, this equation holds. I mean, we can write k to the power p minus 1 divided by 2 as k to the power p minus 1, the whole, like kind of like square root. And we know that k to the power p minus 1 is in fact 1. And the square root of 1 under modular arithmetic p is also 1. Right? Because 1 times 1 is 1, so square root of 1 is equal to 1. That's the idea. So of course, this term will be congruent to k mod t. So this is the square root of, I mean, this is the solution that we are looking for. If the first byte is even, let's assume that, and the square root that we found using this formula is an odd number, we will choose p minus y, the result, as the correct y value for the public key. Okay, if it is even, then, I mean, if the first byte is odd, then we will choose the odd counterpart. If the first byte is even, we will choose the even counterpart. That's the idea. Okay. So now you can ask, right, this p is a very big number. Then how can we compute it? I mean, then p plus 1 divided by 4 is also a very big number. How is it computationally possible to compute this value? Okay, these kind of questions you need to ask to actually understand the cryptographic strength of the scheme that we are using. Okay, like in the cryptography, the idea is that the verification should be fast. Okay, to attack it, I mean, for the attacker, it should be like very hard. It should be computationally infeasible for the attacker, but for the user or the verifier, it should be easy to like find the signature. It should be easy to compute the signature and easy to verify the signature, but it should be very hard to mimic the signature without knowing the secret key. That's a concept, right? So this is the pseudocode, okay, which is used to find the powers effectively. Now, here assume that both A and B are 256-bit numbers. Okay. So we are trying to compute A to the power B. I mean, in Python term, it is A star B. Okay, we are trying to compute A to the power B. Right. So the result will be, the result will be the final answer. Now what we do is we iterate over using the while loop. So now ignore this box for now. What we are doing, we are at every step we are trying to compute A multiplied by A star A. Okay, and we are dividing B by 2. So at every step we are left shifting A. Okay, we are multiplying, not exactly left shifting, we are like finding the square of A, and at every step we are removing a bit of B. Okay, so if B is 1101 in this step, the next step B will be 110. So that's what this dividing does. I mean, you can think of like removing the last bit. Okay. If at the current step it is 110, and the next step it will be 11. Doesn't matter whether the last bit is 0 or 1, that will be ignored right after this step. So the thing is this while loop will run for exactly 256 iterations. Right? Or you can say that it will run less than 256 iterations. So doing 256 computations is very fast. Modern supercomputers can do approximately 10 to the power 18 flops, floating point operations. Right? So doing 256 computations of this form, it is like very, very fast. Now we will update the result only if the last bit of B in the particular iteration is 1. Otherwise we will ignore it. Okay. So now to truly understand this algorithm, try to do what we call a dry run. Right? So choose a value of A, for example 5, and you're trying to find 5 power 3. Now convert it into the binary representation. In binary representation, 5 is 101, 3 will be 11. Okay, and try to replicate this algorithm using a pen and a paper. Then you will understand how this thing works. Right? A is 5, B is 3. So that's now this fast exponentiation is not only used to compute the y value of the public key, it is also used to compute the public key in the first place. Right? So the idea is that in this secp256k1 specification, right? So we have this generator point G, which they claim that this generator point G is kind of like randomly generated. And it is in this is a compressed representation. So this is the x-axis value, and at the leading byte it says 2, which means the y-axis value is the even number. Okay, so in the uncompressed form we have in the compressed form here you have 32 bytes. So this is in the hexadecimal representation. So in the uncompressed form, so this is the y value. The y value it ends with 8, which means it is divisible by 2. Okay, it's an even number. It is randomly generated, and the order of this generator is this particular number. It means that when you g to the power n, you can represent it in this form or n times g. Both means the same, because we are essentially we are computing g plus g till n times. Okay, this is what we are doing. We are doing elliptic addition. So when you add this g n times, okay, you will get the point at infinity. That's the idea. Right? So you can use the same pseudocode here. So here the A will be the generator point, and here the star, it won't represent multiplication but rather elliptic curve addition. So the elliptic curve addition pseudocode was explained in the previous step, right? So the derivation was explained in the previous step. I mean, if you have successfully derived the formula, you know how to write the function in, let's say, Python, for example, and you, rather than multiplying here, computing A times A, there you will compute G plus G. G is equal to G plus G, something like that. Okay, you will call the addition function that you have written. That's how it works. And yes, so it is very easy to create the public key by using the previous thing. Okay, so easy to create the public key, pub key, easy to create the signature, easy to verify signature verification, but given public key, it is hard. Hard means computationally infeasible. It is not even computationally possible to derive the private key. Why that is the case? Okay, I will explain. That we will see in the next video.